Hello, my bomb blowers and module masters, and today I am here with another Keep Talking and Nobody Explodes modded module tutorial, and today I am here with the module Stoichiometry. Stoichiometry is actually a module with a interesting background. It was made in response to the neutralization module not being actual chemistry. I mean, in neutralization you are dealing with chemistry concepts, but the numbers and calculations that you do are kind of arbitrary. But stoichiometry is actually based in real chemistry, and the module actually has you do real stoichiometry that you would do to handle a situation like the one outlined in the flavor of the module. Let's go ahead and get started. This module does require edgework, so I do have the edgework hub on for this tutorial. So,
there is only one perfect solution.
This is stoichiometry.
Clues that will try to trick our team.
This looks like a lot right now, but it's really not that much. Let's go ahead and get started into the solving process. I'll tell you how to handle this thing later, but let's just go ahead and go through the manual. So the deal with this module is that someone has accidentally mixed up the acids that you were working with. Now you need to titrate them with the correct bases before the acids can burn through the table. So what we'll be doing with this module is we're going to be submitting for two different reactions. We're going to have a base and a salt, which we can select using these two selection arrows. You can toggle between bases and salts, and pressing this one will just toggle you to the other of the two reactions. This is actually kind of unnecessary, so I'm not going to use this, and I don't really recommend you use it either. We're going to submit what we have, and it doesn't really matter if it's left or right. You also have these arrows to change this number, similar to neutralization, and you've also got a filter and ventilation button, which we will discuss how to use those later. And then, as you may expect, a titrate button, which will act as a submit button. So the goal for this module is, for two different reactions, we're going to select the correct base, the correct salt, the correct grams of the base, that's what this number is going to be, and we're going to toggle the toxicity filter and the ventilation system if needed. Then we're going to titrate, then we do the same thing for the other reaction. So let's go ahead and get started. The first thing we need to do is identify the acids that are currently burning through the table. And to do this, we're going to go through this flowchart twice. The first time we're going to go through it like you would any normal flowchart. So, let's do that. Does the serial number contain a vowel? You're going to start here in the blue octagon. The serial number does not contain a vowel, so we're going to go down the no path. Does the number of serial number digits are the number of serial number digits greater than or equal to the number of serial number letters? There are 3 digits and 3 letters. 3 is greater than or equal to 3, so we're going to go down the yes path. Is the last digit of the serial number odd? 7 is odd, so we're going to go down the yes path. Are the number of batteries odd? 6 is not odd. Do the sum of the serial number letters exceed or equal 20? So we're going to take the sum of the alphabetic positions of the letters in the serial number. We have hotel, which is the 8th letter of the alphabet. Mike, which is the 13th. This is already 21, which is greater than or equal to 20, so we're going to go down the yes path, which gives us golf for our first acid. Now, for the second time we're going down this table, instead of following the direction that we normally would, we're going to follow the exact opposite. So from here, does the serial number contain a vowel? We already determined that it does not, so we're going to go down the opposite path that we would normally go down. We're going to go down the yes path. Are there any needy modules? There are not, so we're going to go down the opposite path. We're going to go here. Do the sum of the serial digits exceed 12? 7, 14, yes they do. So we're going to go back down the no path. The number of batteries odd, that is false, so we're going to go down the yes path. Are there more lit than unlit indicators? That is false, so we're going to go down the opposite path, and we're going to get Charlie for our second acid. The acids are listed in this table. We have the letter associated with them, which is what you get from the flowchart. You have the name, which I'm not going to be using. Then we also have the formula and the anion. We're going to be noting for both of these acids, we have H2CO3 is the formula. I'm going to put a comma. Next, I'm going to put the anion. Then I'm going to put another comma, and then I'm going to put the charge. This will make it easier for me to organize my data later. You'll see why it is. And then for Charlie, we have nitric acid, which is HNO3. The anion is NO3, and the charge is 1 minus. There is one condition in the flowchart, this one in particular. Are there more modules than the starting time of the bomb in minutes? I am in Zen mode, and Zen mode always starts with 0 minutes, so if you are in Zen mode, the answer to this is always yes. Otherwise, it's if there are more modules on the bomb than there were starting time on the bomb in minutes. So here, now we have determined the acids. There is a unicorn condition here I will go over later. Next, we're going to get the bases. So for the bases, we're going to take a look at the color of the liquid in this tube. It just so happens to be black, which makes it kind of look like there's nothing in the tube, but this is black liquid. So if the color shown in the module is a primary color, red, green, or blue, which it's not, but if that were the case, we're going to take the other two primary colors. So if we had blue liquid, we would be taking red and green. Same thing for a secondary color. If we had magenta, cyan, or yellow, then we're going to take the other two secondary colors. So if we had yellow, we'll take cyan and magenta. Or if the liquid is black or white, then black and white will be used. So we're going to use black and white. If there's an indicator with a matching letter in the phrase get a lab coat, there are no indicators, so this is false. We're going to ignore this. Otherwise, use the lower color for the first acid and the higher for the second. Lower refers to position in the table, not the lower numerical value. So the lower number and the lower position in the table is MgOH2 for our first acid, base even. Mg is the cation, and the charge is 2+. And then for the other one, it is NaH. The cation is Na, and it's 1+. So now that we've determined our bases and acids for our two reactions, now it's time to get into the math. So the first thing we're going to do for all 4 of our chemicals is we're going to determine the molar mass of the compound. So we're going to switch over to the periodic table I have in this tab. So how do you determine the molar mass of a compound? You're going to take all of the elements that compose that compound. So we have, for this one, hydrogen, carbon, and oxygen. And if we look at a periodic table, if you look in the top left corner, over here, you'll notice that there is a number at the bottom of the cell. This is the molar mass of that particular element. So what we're doing is we're summing the molar mass of all of the elements that compose this molecule. When we have numbers after any element, that means we're going to multiply the number in the periodic table by the number to the right of the element. So for H2CO3, we have hydrogen, which is H, 1.008 is the number, followed by a 2, so we're going to multiply this by 2. Next, we're going to go to C, which is carbon, which is 12.011. And then finally, we have oxygen, 15.999, times 3, as there is a 3 after the oxygen, which gives us a molar mass of 62.024 grams per moles. Molar mass is always in grams per moles. Let's go ahead and do this for our other 3 compounds. We have MgOH2. So Mg is 24.305. And here we have OH in parentheses followed by a 2. So we're going to multiply the molar mass of oxygen by 2 and the molar mass of hydrogen by 2. OH is actually a polyatomic ion, hydroxide. But you don't really need to know that. You just need to know that if you get this, you're going to multiply the molar mass of oxygen by 2 and the molar mass of hydrogen by 2. So we have 2 times oxygen, which is 15.999, and then 2 times hydrogen, which is 1.008, which gives us a molar mass of 58.319 grams per mole. Next we have HNO3, HNO3. 63.012 grams per mole. And then finally NaH. We have Na and H, which gives us a molar mass of 23.998 grams per mole. So now that we know how to calculate the molar mass of an element, I'm going to return to that unicorn I mentioned earlier. If you have exactly 2 batteries in one holder and a lit FRK indicator, then you have created azide, which I'm pretty sure is not a thing that exists, but maybe I'm surprised by how much research went into this module. So, in this case, this is the last thing you need to even consider in the manual. So what you do for this is you go through the flowchart we went through earlier to get the first acid. So for this module, it would have been H2CO3. And then we would take the molar mass, remove the decimals, and then submit. We're going to press titrate, not even changing anything, doesn't really matter what's on the module. You're going to press titrate when the last 2 second digits are equal to this truncated molar mass. If we had 58 or 23, if we had 58, then we would press it on the last 2 second digits being 58, or if we had 23, last 2 second digits 23. But for 62, this is over 60. So what we would do instead is to calculate the digital root of the molar mass. I'm sure you know what digital root is by now if you're this far into the community, but if you don't, then the digital root is just taking the sum of the digits until the digits are a single number, which would be 8 for this case. Then we're going to press titrate when the last 2 second digits are 0, followed by the digital root. But that's not the case, that's just going over how the unicorn works. Let's go ahead and get back to the calculations. So we have the molar masses. Next, we're going to need to get the amounts of acids that we have in grams. Based on the day of the week, we're going to do a modification, but the normal amount of acid that we have is 16 grams for the first one, and 20 grams for the second. It is currently Friday for me, which just so happens to be the easiest. Your boss was feeling lazy and giving, so he just ordered the normal amount. Which means that we're going to be dealing with 16 grams of our first acid and 20 grams of our second. Let's say that it was Tuesday, for example. He was feeling particularly mean and ordered 7/5 a normal amount. So what you would do in this case is you would take first the 16 number, then multiply it by 7/5, and then instead of 16 grams, we're dealing with 22.4 grams. And then we take our second number, 20 grams, multiply by 7/5, and for the second, we would be dealing with 28 grams. Okay, so now that we have determined we have 16 grams and 20 grams, we now have all the information we need to calculate the answers to the module, except for this part, which we'll get to later. So we're going to go to the textile calculator. I'm going to establish 3 variables. We have, first of all, the molar mass of the acid. I'm only going to be considering this first one right now, so we're just going to ignore this for now. So the molar mass of our first compound, the acid, is 62.024 grams per mole. The molar mass of the base is 58.319. And the grams of the acid is 16 grams. We're going to convert from the we have the mass of the acid. We're going to need to convert this to the moles of the acid. So moles of acid, what we're going to do is, to get from 16 grams, we're going to divide it by the molar mass. How this works is that let's do this. If you imagine that we have two fractions here, we have 16 grams here, and if we put our grams per mole here, we have 62.024 grams per 1 mole. This is sort of a ratio. So 62.024 grams over 1 mole. These two are the numerators, and these two are the denominators. If you have the sum of anything in the numerator and denominator, they cancel out. So what happens here is that the grams cancel out, leaving us with only the moles as our units. And then we're going to multiply these two fractions, 16 times 1 over nothing times 62.025, which gives us a fraction of 16 over 62.024, which will give us the moles of the acid. So that's the proof of how this works. If you just want to know what to do, you're just going to take the grams of acid and divide it by the molar mass of the acid, and you have the number of moles now. Okay, now that we've gotten the moles, we're going to calculate a molar ratio. The molar ratio states that per X moles of acid in our mixture, we have X moles of base. So to calculate the molar ratio, we're going to take these numbers that I got earlier. This is why I put them in a comma-separated list. To get the molar ratio, you take the number attached to the minus, which is a... Okay, what the hell? That was weird. Anyway, you're going to take the number associated with the minus and divide it by the number associated with the plus, and this is the molar ratio. It just so happens to be 1 because both of the charges on our atoms were 2. But if you had something like... Let's go back to the acids for a second. We had something with a 2 minus charge. If you had something with a 1 minus charge, then it would be 1 over 2. So the molar ratio would be 0.5. Or if you had this, where is it? Here it is, PO43 minus. It would be 3 over 2, so it's 1.5 instead. Same thing applies to the bases. Let's change this back to a 2. There's only one base in here that is 2 plus, and we just don't happen to get it. But if you had 1 plus, for example, the molar ratio would be 2. Alright, so now that we've established the molar ratio, we're going to get the moles of the base. My bad, I should be using N because this is how moles are notated in actual chemistry. Moles are usually notated with the letter N. So the moles of base is going to be the molar ratio times the moles of the acid, which gives us this. This makes sense because it's saying for every 2 moles of our acid, we have 2 moles of our base. So it's saying that we have an equal number of moles of our base and our acid. Finally, we can get the mass of our base. And this is the number we're going to be submitting to the module. So to get the mass of the base, we're going to take the moles of the base and multiply by the molar mass of the base. This gives us a number in grams, which is 15.044. So now let's go ahead and start submitting to the module. The number we're submitting is equal to this number, rounded up. Always round up. So we're going to be submitting 16 grams. Let's go to bases, and then we're just going to submit whatever base we have, which is MgOH2. Next, let's switch to salts. And then to get the salt, we're going to take both of these two and smash them together. You're going to notice that all of the salts all start with the cation that we got earlier. So this is how to double check that you are right on your base. If they all start with the cation, then you know you have the right base. And then we're going to put CO3 at the end. Here it is. And then finally we're going to go to this table. This is simple. We're just going to take the intersection of our acid and base. We have H2CO3, which is here, and then MgOH2, which is here, and we get a V. So if you get a white cell, you don't change any of these, just leave it as is. If you get a V, you just turn on the ventilation system, which we're going to be doing, and if we titrate, it did not strike us, and it played a nice sound. That means that our first reaction was correct. But if we get a T instead of just toggling the ventilation system, we're going to toggle both the ventilation and the filter. If you get a T, toggle both. If you get a V, just toggle the vent. And if you get a white cell, don't toggle either. Okay, so we're going to be doing the same process that we did with the previous reaction, but instead with 20 grams, and we have different molar masses. We have 63.012 and then 23.998. So to get the moles of our acid, we're going to take the grams of the acid and divide it by the molar mass, which gives us our number in moles. We're going to take the molar ratio. We're going to take the number by the minus and divide it by the number by the plus. To get the moles of our base, we're going to take the molar ratio and multiply it by the moles of the acid. And to get the mass of the base, we're going to take the moles of the base and multiply it by the molar mass, which gives us this. So this is the number of grams that we have. 7 rounded up is 8. Our base is NaH. Oop, we're on salt still. Next, we're going to go and smash them together. We're going to take the Na, which is at the start of all the salts, and we're going to put NO3 at the end of it. NaNO3. And then we take our intersection in the table. We have HNO3 here, and then NaH here, which is the vents. And when we press titrate, that is a solved module. If you have any questions, please feel free to put them in the comments below. This is a rather complicated tutorial. I did take an entire year of chemistry classes in college before I understood how this module actually worked. So please feel free to leave any questions in the comments. I'll be sure to answer them, even if I'm not in the community. So thank you for watching the tutorial, and have a nice day.